Okay, we're going to go one step further, one step beyond what we just did on the previous lesson. We're going to do the same thing. We're going to graph lines. We're going to graph inequalities, actually. We're going to shade. We're going to find the feasible region. But then we're going to take the corner points, all the corners of the intersection that outline that shape, whether it's a triangle or quadrilateral or whatever, and then we're going to test those points in an equation and see which one maximizes or minimizes the value. This is called linear programming, okay? And it's used in businesses all the time. And what we're doing is, it's a method of finding a maximum minimum value of a function that satisfies a given set of conditions called constraints. The constraints are the inequalities the lines of inequality that we draw, okay? The solution to the set is called the feasible region. We talked about that in the previous lesson. So it's used in business, biology, economics to find the maximum or minimum value of a function that also satisfy a set of restrictions or constraints. So it's got to be within the region in this area, but also maximize or minimize. A corner point is a point in the feasible region where two lines intersect. So here are the steps. Kind of already went over them. Graph the inequalities to find the region. Identify the corner points. Plug those points in the objective function, which is z equals, and then determine the maximum and minimum value for z at which the corner points occur. So here we go. The following graph shows a region of feasible solutions. Use the region to find the maximum and minimum values for the given function z. So again, let's say we drew a line and it went like this, and we had another line and it went here, and we had another line and went here, and another line went here. And then when we shaded all four inequalities, we ended up with this area here in the middle, this quadrilateral. And when we looked at the 4 points of intersection, it was 4, 1, 7, 4, 3, 8, and 0, 5. Now, we're going to do what we just did in the previous 7, 1 through 7, 5 when we were evaluating points to see if they were the intersection, the solution of a system. Similar idea, we're just going to plug all four of these points, although into just this one equation right here. So we're going to plug in 3, 8. Okay? Z equals 3 times 3 plus 2 times 8. So z equals 9 plus 16, which is 25. 7, 4. Z equals 3 times 7 plus 2 times 4. 21. Z equals 21 plus 8, which is 29. We're going to plug in 0, 5. Z equals 3 times 0 plus 2 times 5. So z is equal to 0 plus 10, which is 10. And last but not least, we'll check 4, 1. Z equals 3 times 4 plus 2 times 1. Z is equal to 12 plus 2, which is 14. So our maximum is at 7, 4. And our minimum is at 0, 5. Okay? Now we're just going to do it again. Okay, we're going to plug in 3, 8. Z equals 3 plus 4 times 8. Z equals 3 plus 8 times 4 is 32. That's 35. Let's go the other direction. I'm going to do the 0, 5 now. Z equals 0 plus 4 times 5. Well, z is equal to 20. 4, 1. Z equals 4 plus 4 times 1. Z is equal to 8. And last but not least, z is equal to 7 plus 4 times 4. That's going to be 16 plus 7 is 23. So on this second one, Again, 7, 4 is our max. This is for A, and this is for B. Nope, I lied. 35. Just see if you're paying attention. 35, which we get from the point 3, 8. So our actual maximum on this one, on B, is up at 3, 8. And our minimum is at 4, 1. That's for B. Okay? Now, start to finish. Okay? We're going to find the minimum value, the minimum, we're just looking for that, for z equals 4x plus 7y. So we're going to graph these. Okay? So whatever works for you. Now, here's a nice easy one. This tells you greater than x, greater than y. When you see these two together, it means we're only going to be in region 1, right off the bat. Only region 1. So personally, I don't even shade those. I just know it's going to be in region 1, so it kind of reduces all the clutter for me. So I'm going to rewrite these. Now remember, there's two ways to do x minus y greater than or equal to 1. And I want to go over both of them just to review it for you. I can move the x over by subtraction and get negative y is greater than or equal to negative x plus 1. And then I need to divide by negative 1. And hopefully some alarms are going off in your head from the beginning of the year when we talked about inequalities. When you do this, you need to switch the sign. X minus 1. Okay? You got to change the direction. Whenever you multiply or divide by negative, the inequality switches. A way to avoid that would be to move this over that way and move this over that way. And what you end up with is y is less than or equal to, again, x minus 1. And if you're more comfortable seeing it this way, you end up with the same thing. Okay? So now I'm going to go ahead and graph that. My y-intercept is negative 1. Okay? My slope is positive 1. That means up 1, right 1, up 1, right 1, and so forth. So I'm not even going to worry about down here because I know my only answer is in region 1. Okay? And I have to test, don't forget to test. I want to plug in 0, 0. And I'm going to say 0 is less than or equal to negative 1. Well, that's a lie. 0 is greater than any negative number, which means I'm going to be shading this half of the line. Okay? But remember, just to make it a little less dramatic, I know I have to stay in region 1, so I'm just going to shade right there. There's region 1. Now I'm going to do my other one, 3x plus 2y greater than or equal to 18. Move that up here. First off, I need to move the 3x over, so that gives me 2y is greater than or equal to negative 3x plus 18. Divide everything by 2. Y is greater than or equal to negative 3 halves x plus 9. Okay, change color. Y-intercept of 9. Down 3, 1, 2, 1, 2, 3, right 2. Down 3, 1, 2, 3, right 2. And look, I got an intersecting point right there. 1, 2, 3, 1, 2. At this point, I can just go ahead and draw my line. Notice these are all solid lines. And you can almost bet where the region is going to be because we're trying to find an enclosed area, but not always. So let's test real quickly. I'm going to test 0, 0. 0 is greater than or equal to 9. True or false? Well, that is false. So actually, okay, we're going to go back and make a change. We're going to change this to less than or equal. Okay. Less than or equal, less than or equal, less than or equal, which is going to give us the statement 0 is less than or equal to 9, which is true, which means I'm going to shade everything underneath here. Okay. Which means my feasible region is this triangle right here. And then my points, my corner points are here, here, and here. So my corner points are at 1, 0, 6, 0, and 4, 3. Now I'm going to plug all those in to z equals 4x plus 7y. So I'm just going to do it in my head. 4 times 1 plus 7 times 0 is 4. 4 times 6 is 24, plus 0 is 24. And 4 times 4 is 16, plus 7 times 3 is 21. 16 plus 21 is 37. Okay? Now since we're trying to find the minimum value, that's right here at 1, 0. So 1, 0 is the minimum value. Okay. X plus 4y is less than or equal or is greater than or equal to 12. When I rewrite this, it's going to end up being y is greater than or equal to negative 1/4 x plus 3. Again, you move the x over, and that's going to make it negative. Divide by 4. There you go. So plus 3 right here. Negative 1/4. Down 1, 1, 2, 3, 4. Down 1, 1, 2, 3, 4. Up 1, 1, 2, 3, 4. Up 1, 1, 2, 3, 4. And there's my line right there. When I test it, I'm going to plug in 0, 0 and get 0 is greater than or equal to 3, which is false, which means I'm going to shade above the line. Switch colors. The next one is going to end up being y is greater than or equal to 1/2 x. I'm going to put plus 0 just to remind ourselves it's going through the origin. So that starts here, goes up 1, right 2, up 1, right 2. There's an intersection, up 1, right 2, up 1, right 2. I can't test 0, 0 because it goes through, even though my line's horribly drawn. It goes through. So I'm going to test 2, 0. I could test 1, 0, but since I'm going to multiply by 1/2, I'm going to plug in 2, 0 to test. And I'm going to get 0 is greater than or equal to 1/2 of 2 is 1. 0 is not greater than 1. So I'm not going to shade it above the line, below the line. I'm going to shade above the line. Okay, so right now my feasible region is above the red and above the green. You can kind of see where they overlap right now. My third one is going to be y is less than or equal to 1/2 x plus 3. Move the x over by addition, divide by 2. There you go. I'm going to test 0, 0. And I'm going to get 0 is less than or equal to 3, which is a true statement. So let's go ahead and graph that. Again, going through 3. But this time having a positive slope of up 1, right 2, change colors. Up 1, right 2, up 1, right 2. That's going to be a parallel line right there. Now since 0, 0 is true, I'm going to shade below the line. Now none of this really matters because I know I have to be above red and above green. So really, I can see that it's going to be somewhere in this area right here. because that's where the red and green is. So I kind of start cleaning up my shading to make it easier on myself. And last but not least, x is less than or equal to 6 is a vertical line through 6. Everything left of that. So where am I going to be? I'm going to be in this region right here. So I'm going to be in this kind of quadrilateral right here. So what are my points of intersection? They're going to be right here, 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 and here. I know it's kind of blurry, but those points are 0, 3, okay, 6, well, 4, 2, it's underneath, 4, 2, 6, 3, and 6, 6. And now I'm going to look to try to find the maximum and minimum values of x plus 10y. So z is equal to 0 plus 10 times 3, 30. Z is equal to 4 plus 2 times 10, that's 24. Z is equal to 6 plus 30. And z is equal to 6 plus 60, 66. So my minimum value is at 4, 2, and my maximum value is at 6, 6. There you go. Okay, real quickly, I want to go back up to example number 2 and talk about what would have happened if we didn't change the sign. Okay, so I'm going to just kind of draw region 1 right here. Imagine that's region 1. Okay, and we had our first line that looked like this. And we had our second line that came through and looked like this. Okay, and you can see the little triangle that we ended up shading until I change the sign. Well, if I did not change the sign, okay, then it would have been like we did originally, underneath here, and it would have been the other side of the green line, which would be here. So where would the area of feasibility be? It'd be right here. And this is called an open area. And that's okay in this case because we're trying to find the minimum. Now, if this problem was asking for the maximum, it would not work. We would have to change the sign or find the error somewhere else. But since we're finding the minimum, it would still work because we have these 2 points, which would be our 6, 0 and our 4, 3, okay, which we've already plugged in. And 6, 0 would give us 24, 4, 3 would still give us 37, and then we'd find out that our minimum would be right here at 6, 0. So just so you're exposed to it,